So this is our fourth and final section of 1.3 where we define and look at anomalies of floating point numbers. And the topics here are going to be called gaps, underflow, overflow, and significant digits. And we'll start off with gaps. Now, what do you mean by gaps? Well, we are using a finite number of numbers. There's a set of strategically used rational numbers that we're storing on a computer that have gaps between them because you have a fixed number of significant digits that you can deal with. Let's go back and look at that mantissa. There's 23 bits. That 23 bits of the mantissa is really determining the precision to which we can store any number relative to its size. It exists as a binary number in the computer, and if you fully loaded it up from left to right with ones, all 24 of those bits, even after you stick that fixed one bit on there that builds the significand, then that number, if you converted it to decimal, would be a little over 16 million. Now, on first blush, you might be a bit disappointed with that. I mean, if I thought that the biggest number I could create in computer memory was 16 or 17 billion, I would realize there's a lot of applications that I can't use computers for. So that's not really the point of this exercise. What we're looking at here is how many combinations of numbers can you put in the mantissa. Don't forget that the mantissa is always multiplied by 2 to some exponent. So that's how we're scaling that thing up and down to form big numbers and little numbers. But relative to the size of the number really being more tied to the exponent, the digital accuracy is contained in the mantissa. So if we take a closer look at that number 16.7 million, what we see is that it used 8 decimal digits, but it missed a lot of combinations there. I mean, anything from 1.7 million above isn't listed in this number of combinations that can be stored in the mantissa. But if you only used 7, the rightmost 7 digits, and didn't depend on one of those digits, then you could fully cycle through all possible numbers up to that range using the 7 digits. And so that is what we are going to end up calling our significant digits for single precision reals. Now, if you take an even closer look at this, you might complain that in fact you don't really have 24 bits, because that red one never changes. The variability can only take place in the 23 mantissa bits. But we're playing a game with the exponent so that by the time we run out of space here and we need to move upward, we are just shifting everything by 1 bit to the left and holding that result in the exponent, giving us really this full 24-bit usage of the mantissa, or in this case, the significand, by the time we add that red number on there. It does come with a minor price. The price is that we won't get quite the range of data, either tiny, tiny, tiny numbers or gigantic numbers, but it's a very small price to pay because you're only losing data on the very extreme ends of your numbering system and giving yourself a whole nother digit to work with. Okay, so because now we see that there are only 7 reliable digits of accuracy in floating point notation, or at least single precision floating point notation, that forces gaps between numbers. Think about any 7-digit number you want and put a decimal point in front of it and just add another 8th or 9th digits. I mean, the numbers are there. We just can't use them on the computer. So you might get a little nervous about that. In fact, I get a little nervous about that. We're going to fix that problem, or at least significantly fix that problem a bit later. But before we do, keep in mind that it's about the best job we can do. We want numbers to be useful, whether they're measuring things on an atomic scale or whether they're measuring things on a astronomical scale. And if you're trying to measure things in parsecs, or you're trying to look at light years as your basic measure of interest, if you're off by a few 100 million miles, nobody's going to care because your focus is on a larger distance in that case. On the other hand, if you're looking at the distance between the electrons and the proton of a hydrogen atom, certainly being off by miles isn't going to be very useful. But the self-scaling nature of the exponent allows the accuracy to be relative to the size of the number, and that's why it's important. So these gaps between numbers are always uniformly spaced within the mantissa, but as you're increasing the exponent size, the gaps are getting larger by the same proportion. The mantissa is getting shifted to the left and the exponent is decreasing. If it's going to the right, then the exponent is increasing. And that is being multiplied by the gap in the mantissa so that the actual real floating point number associated with it is changing proportionally as well. That brings us to needing to define some additional terms. One is called overflow, one is underflow, and one is called machine error. Overflow exists when you have built up your exponent as big as it can go and you try to make it yet go bigger. The machine is going to come back with an error and say, I can't get a number that big. The same thing's going to happen if you try to go too small. So if you take a number and run it down to the smallest possible exponent you can have and try to make it smaller, then you're going to get what's called an underflow. So let's take a look at an example using an underflow. Here is the smallest number, or the smallest positive number, that I can construct in floating point notation, single precision floating point notation. I've got a positive number because I have a 0 in the sign bit. This exponent is as little as I can go. The reason for that is if I make it all zeros, that's a reserved error code that I'm not allowed to play with if I'm really talking about actual numbers. So here's my smallest exponent. To find out what that is in decimal, I need to subtract 127. And the scaling would be 2 to the minus 126. That would be quite a small scaling. All of these zeros in the mantissa will get preceded by a 1 when I form the significand. And so that then turns into the number 1 itself, because this 1 is in the 0 location of the binary list of numbers. So this whole thing turns into 1.0 times 2 to the minus 126, which is a really tiny number, which we'll call the machine error. That epsilon sub m, machine error, is the point at which if you tried to go any smaller, you would be in a region that your numeric representation just didn't know how to deal with it, and you're going to get an error. An error is going to appear in this code here. It's going to be all zeros saying that you've just underflowed and you don't know what to do with that. Same thing happens on the negative side. If you try to go between 0 and minus epsilon sub m, you're going to have an underflow condition, and that will end up storing a code in this exponent. On the large side, if you try to create something that goes beyond your ability to represent in this floating point notation, you'll get all ones appearing in this exponent here, and that's called machine overflow. Any attempt to use a number that's invalid, whether it's underflow or overflow, will result in what is called a not a number, NaN. And your exponent will be all zeros when that occurs. There are some subcodes too that happen that the IEEE standard will play around with the first 2 digits of the mantissa to tell you a little more about what happened. But the long and short is that your goose is cooked because you can't go any further once you have killed your number in that manner. What your book says is if you take the real number 1, I didn't say floating point number, I said the real number 1, and you add some very, very small number to it, And after you add it, you apply the floating point rules of addition. If you get a 1 back, then this number must be within the machine underflow limits, or the machine epsilon. If you make this number even the tiniest bit bigger, and you end up doing the floating point addition and get a number bigger than 1, then that means you hit the machine epsilon right on the nose. So it's that boundary point at which you will get no change in the operation, but if you had made the number even slightly bigger, you would have detected a change in the floating point numbers. So that is your book's definition of machine epsilon. Okay, I've alluded over and over that these problems seem to come with the term single precision real. And I am not real happy with only 7 digits of accuracy. I think we should do better than that. And so let's see if we can't rethink our floating point operation using 64 bits rather than 32. Now you're going to have a homework coming up where you're going to get to do this instead of me. So this is one slide to help you get started. You recall we had 4 groups of 8 when we had single precision real. So we're going to double that. We're going to give you 8 bytes, or 8 groups of 8 bits, and call it either 64-bit floating point, or you could call it double precision real. Now that's a big deal in old days because that took software to create that for you. All modern computers now are 64-bit arithmetic, so this has really become the standard rather than something you'd have to create in a compiler. But this is how it's going to work. It's going to work exactly the same way as a single point. It's just you have more bits to work with. So we'll break this structure again into a sign bit, into an exponent, and into a mantissa. The exponent, however, we're going to give 3 extra bits to it, so we'll have 11. There is no point in giving any more to the sign bit because you just need to know if it's positive or negative. 1 bit is enough. But by getting 11 bits in the exponent, you are now multiplying by 8 the size that this number can be. And when you take 2 raised to that power, you've greatly expanded the scale in which your real arithmetic can work. What's even better is that the mantissa has become huge. Where we only had 23 bits before, we now have 52. We'll do exactly the same thing we did with single point real. We'll add that leading bit of 1 for the exact same reason. So you really will have 53 bits to work with in forming that. If the leftmost bit is 1, same thing as before, it's a negative number. If the leftmost bit is 0, it's a positive number. We also need to divide all possible numbers in the exponent into 2 groups, a positive group and a negative group. Now we're going to need to keep one around for 0, and we'll need the same error codes that we had before, so it'll completely mirror what we did with single precision, but the middle point becomes 2 to the 10 minus 1, and that is equal to 1023. And anything below 1023 will be negative, anything above it will be positive, completely in an analogous manner to single point real. So let's go to homework number 3 and see what we need to do. First thing I want you to do is rethink that whole 64-bit world using the 32-bit as a model and find out how many significant digits you're guaranteed to get using double precision real. Go to your book in normal exercise 1.3 and look at problem 5H. Then I want you to create a 32-bit representation. So now we're back to the single precision world for the number e. So I basically reproduce what we did with pi and see if you can represent that thing in single precision real. Finally, as extra credit, you can go back to section 1.3, again the normal section, not the computer section, and do problem 15. So we've now really beat to death floating point numbers. You know everything you need to know about them. We're going to look at our first problem next time when we get into 1.4, where we're going to be booby-trapped by the very nature of real numbers when we just simply try to do a subtraction. Something as easy as subtraction, we're going to get shipwrecked with a loss of significant digits unless we're very careful. So we'll see you next time.